All right, let's talk about navigation. And we're going to have to talk about history a little bit. The first kind of navigation for aircraft, but also mankind in general, it could be termed pilotage, except that implies that's what airplane pilots do. But we're all familiar with this. You look at particular landmarks to navigate. When you're on the way to the school, you turn left on this road or right on that road. You recognize it visually by the landmarks, right? There's an office building there, and this is the second traffic light, etc. Pilots at the very beginning of aviation used the same methods. Of course, at first, aviation was just okay, let's just jump in the airplane and fly around. But then they had to figure out some way to make money. Delivering mail was one of the early ways. Delivering passengers, of course, developed in a little bit of time. But so in the early days of aviation, pilots would fly along, and they on their little notepad and they just write it in a little pad. This particular landmark, significant looking landmark, like a river or a road or a town or something like that, and that's how I get from A to B. From when I leave my destination airport to go to another airport, actually. In the early days of aviation, it was one field to another field. It wasn't even an airport. They'd have it in a little notebook. As they started developing and they wanted the reliability of delivering mail and of course the safety and reliability of delivering passengers, they built airports. Well, how do you get from airport A to airport B? They tried a couple of different ways. One of them was actually to paint arrows on the roofs of barns with the initials of the airport that was pointing towards, so pilot could visually see that. So pilotage is a visual way of navigation. Um, Later, they developed a light signal kind of thing, light rotating beacon kind of things, where pilots could look at that flashing light, and that, of course, is just very similar to the nautical navigation as well, right? We have flashing marker beacons and signs, etc. So pilotage is something that is a holdover from the old days of sailing and shipping as well. Of course, that works great for land, but how about going over the ocean? Well, historically, one of the first uses of long distance over ocean flying was developed by the cruise ships, because they were delivering not the kind of cruise ships for parties, but the kind of ships like the Titanic and etc. Many of them were sailing across the ocean to go from Europe to America or the other way around. How did they navigate? Well, they would navigate through celestial navigation. Cruise ships, naturally, this was pre-airport, major airports. They developed and they financed the development of seaplanes or flying boats, basically. So they would have to navigate across long distances. Well, they used what the early navigators, ocean-going navigators, used was sextants and basically celestial navigation. They'd take moonshots, or they'd have a book to tell you where this planet should be, how above the horizon it should be at any particular time, and it was not very accurate because we're bouncing around a little bit, but it was accurate enough to get across the ocean and pretty accurately and get to where you want to get without running out of gas, because they're limited amount of fuel as well. So you can do some investigation that on your own. That's not used very often, but it's still a useful backup for navigation. So then, as time went by, we developed some electronic means of navigating. On the right-hand side, you see a chart, sectional chart. We're familiar with that already. And you'll notice there is a magenta, like a lot of dots around that airport. That signifies that there is a radio transmitter there. And, oh, I have a pen here. Let's see if I can use my pen. I'll use red. So you look over here, it says Aiken 347, and then it has AIK, and then the Morse code for AIK. So you tune that frequency into your little radio, and the needle would point to that station. So hey, this is a way to get to Aiken. You just point that needle straight ahead. You fly towards that needle. This is very early radio navigation. It's called radio direction finding, or ADF navigation. Doesn't not correct for wind. It all it does is point to the station. So there's some calculations that might need to be done if you want to fly in a straight line and not. But that's beside the point. These are basically AM stations. So just be aware, AM stations, well, I don't know if you guys are familiar with AM. You guys use FM, a higher frequency. AM is susceptible to lightning or any kind of electrical interference. The needle will point different ways. But anyway, this is one of the early ones. It's primitive, but very useful still. Then we developed something a little more accurately. So you'll see this on charts, sectional charts. It's the Augusta area. It's in blue. So this station here, right there is the station. That's the point, and it's this one is associated with that. Collier's is the VHF omnidirectional range navigation station. Okay, so it points. It has specific radials or bearings. Bearings would be to the station, so you know you'd be on this line if you tuned it in and it said, let's see, there's north, this is north, that's the arrow points north, 10, 20, 30, 40, 50 degrees. So this would tell you you're on the 50-degree radial away from the station. So now you know specifically where you are. You're on that line, and if you keep that needle in the center, you just follow it down and get to the station. So it's so much more specific. It basically magnetic bearings, north 360, and then there's 180 down here, 90 over here, 270, right? So there's basically a compass rose associated with that navigation facility. That's all it tells you. This is not an airspace marking. This circle doesn't have anything to do with airspace. It has to do with navigation. So when you see that, don't get confused with all of the navigation areas. So that's one of the ways. So getting more specific, great. So, and here's a demonstration of what you can do with those things. You can fly to it or away from the station. Interesting. But here's an even more clever use of this is you can cross-check two different VORs. The VORs are all over the country. You'll see them all over charts. If you receive two of them, you can find out exactly where you are by cross-checking it. This is an important concept, cross-checking or triangulating your position. You might possibly have a third one, and you'd be able to get really accurate. The more of these different, this one, if there's three of them, it gets even more accurate, and your position gets closer and closer to be where you really are. But these are pretty accurate. Even if you had two, you'd be fine. But then we look into global positioning, which is the next step, which has made it even more accurate because this, of course, VOR navigation, NDBs or non-directional beacons do not give you altitude. GPS will give you that as well. So I'm going to ask you to watch the video. I can't show it to you on this, but if you'll watch the video that's on this lesson, you'll be able to learn a little bit more about that, or at least review, because you probably do know something about it. Now, so how do you see the GPS positions on a chart, a sectional chart? Well, they'll be listed, to make it easier, they'll be listed like this one here, Lily. That's an intersection. You'd be able to possibly put that into your GPS receiver, and it will tell you where that intersection is. There may be more than one Lily. There might be another one in Afghanistan. I don't know. I'm just saying. So it might ask you, are you talking about the Lily in Afghanistan, or are you talking about the Lily in America? So you have to be careful to discriminate between that. There's another one over there, Lump. So they're listed on the chart. GPS essentially uses latitude and longitude. There's a longitudinal line, 84 degrees, right, west. The latitude line, I don't see one here. Remember, latitudes go like that. So, and latitude and longitude goes like that. But anyway, that's how they're expressed, though. And essentially, it would be latitude and longitude lines. They've made it simpler by giving these names to the intersections or fixes. There's governor, et cetera, et cetera. So, like I said, look at the. So now we've got a lot more accuracy. Let's see here. Yes, I got to erase this. Let me see. Okay, here's a listing of some intersections here. Cotton 1, there's the latitude and there's the longitude of that fix. So you can actually find that out if you need it. If you had a very crude global positioning system receiver, you might have to punch those numbers in there. Punching those numbers in there is fraught with danger because human beings are not very good at accuracy sometimes, especially, I mean, there's all kinds of factors. We've talked about that before. If you're in a hurry, if you don't have a checklist, there's lots of reasons why you can screw this up. Case in point, here we go. Korean Air flight from, let's see, it was from Alaska to Seoul, Korea. It was, you can look it up yourself. It's Korean Airlines Flight 007. Was flying before this was early on. This was what? Let me see, 1983. There was a number of human factor errors in this particular accident, but en route from New York to Seoul, Korea. So New York had to stop to get fuel in Anchorage. It got the dash line is what they were supposed to be doing, but the way they entered the latitude longitudes for their GPS signal entered them over Russian airspace. So Soviet Sukhoi Su-15 flag-on fighter spotted this. I guess they saw it on radar first, and so he was scrambled to go out there and check out. He did a warning shot, but then apparently the 747 crew, Korean flight 007, did not see the warning shots. So, and for some reason they didn't use pilotage, right? They could have looked out the window and noticed that they're over land. There's several opportunities for them to notice that and make corrections, but anyway, they got shot down with a bunch of passengers too. So I can't remember how many passengers perished, although there was a senator, U.S. senator on board, so that made big news headlines. By a simple mistake with latitude longitude. So that's why we've made some changes. The aviation industry has made some changes with crew coordination and human factors, but also let's make these fixes a little bit easier. Let's have some double checks too, because humans are not very good at this. Okay, so anyway, just wanted to point that out. So moving right along. With navigation, we mentioned latitude, longitude. Just remember, this is an important concept. The prime meridian, does it mention that? Well, it's way over here. Yeah, oops, let's see. Prime meridian's over here, goes through Greenwich, England. That's where zero time is. Not coincidence. This is where we mark zero time. Everything else you have to correct. And then we're heading west. For these meridians, or the lines of latitude, we're heading west, so it's, 15, 30, 45, 60, 75, 90 degrees west. You're going to the east, Middle East, India, China. Now we're east around the globe. Not only that, but then we have these lines of latitude which go this way. The equator is latitude 0 degrees. And so 15 degrees, 30 north, 45, 60, 75, then north is 90. And you see it's 90 degrees. So it's a little bit of geometry there, but anyway, 90 degrees. So latitude, I like to think of it as a ladder. And latitude like a ladder, then longitude being east and west lines. And here's the edge of the chart. So you can see here on the edge of the sectional chart, we have 35 degrees. So that's 35 degrees north, because that's where we are. This is a chart from our area here somewhere. So 35 degrees north would be somewhere along, and this would be this one, would be that line there. 35 degrees, well, that looks like Atlanta. To me, it looks pretty close to Atlanta. 35 degrees, 30 minutes. 36 degrees. Comprendo? Chicago is 42 degrees north latitude and 88 degrees west longitude. Let's see, 90 degrees, so Chicago is right about here. So 90, so 75, 88 is this one here. 88, 90 latitude. We'll practice this in class because it's a little bit obscure, not terribly obscure, but it's a little difficult concept. But this gives you an idea of what we're talking about. The chart supplement U.S. indicates. So if you want to have if you have an airport, it lists the latitude and longitude of the airport. If you want to find that airport, we have latitude and longitude. So it's like an index to find on charts to find out where something is that you're wanting to go to. Your grandma's house has a latitude and a longitude. It's not published somewhere, probably not, but it has a latitude and longitude. So if you want to go fly over that, well, you can set that into the GPS receiver and it will take you right to that spot. Or your favorite fishing spot. If you're an ocean fisherman, you have your GPS unit on board the boat and you mark that spot, and you're marking a geographical position so that you can go back there and fish 6 months from now when fishing gets better, perhaps. Right? So that's one way that you can use latitude and longitude information. We have lots of samples here. Just looking again, we have, okay, so here can be a confusing thing. Okay, 85 degrees. Now we know it's west, and we know going that way gets bigger, and going this way gets smaller. So 85:30? No, it's 84:30 minutes. So if we wanted to find Marion County Airport, one of the places it's going to be pretty dang close to 85 degrees 30 minutes west longitude, and then all I got to do is find the latitude line here. I don't see a latitude line. It's the way I cut this chart off. I can't find it here, so we would nope, it's not there. But anyway, the actual position of Marion County is, and I've got it right here, for minutes it's 32 degrees 16 minutes would be, of course, north. It'd be one of these lines here. All right. 32, 6, and I do not see a 32. It could be here, and I'm just not seeing it, but nope. Okay. Okay, latitude and longitude also is related to time zones. Every 15 degrees of longitudinal lines, we have a different, generally speaking, have a different time zone set up. Now, some of them, the lines aren't exactly straight because you want a whole country or a whole state to be in the same time zone. So there's some zigzags out there, but basically every 15 degrees there'll be another time zone. The planet is turning. We all want to. If in agricultural society, you get up when the sun comes up and you go to bed when the sun goes down. But we actually, in our modern technological society, we sort of need to get straight. So it was basically originally for navigation purposes, but now it's so that when we look at a weather report, we don't have to do a fancy calculation. Well, that weather report was formulated in Denver, but I'm here, so I got to calculate. No, it's all going to be written in Greenwich Mean Time. Then all we have to do is the other opposite kind of calculation. 6 hours, add 6 hours, and that gives us the local time. So we're all on the same page as far as weather reports, when they were published, what their effective dates were as well. There's some other reasons for this, having time zones. Human beings are based on that rhythm of sun comes up, sun goes down. Dark, we tend to sleep, and light, we tend to be awake. That's going to, of course, be an issue for space travel since it's going to be light all the time. But there's ways to mitigate that problem. But so just keep that awareness. We have 24-hour clock as well, so that we can easily distinguish between AM and PM. Instead of having to write AM and PM, we just use, if you say 300 hours, that's 3 o'clock AM. If we say 1500 hours, that's 3 o'clock PM. So think that through as well. Another navigational issue we need to be aware of is that, the Earth is a magnet, and the magnetic north is not the same as the geographical north. So all of our charts are based on geographical North Pole, the pole which the planet is rotating on, basically, because that's the only way it would make sense for time zones and navigation. So planet has a North Pole that's geographical, which means that's the axis where the Earth is rotating. And then we have a magnetic North Pole, which is somewhere in Canada. So we have lots of lines of variation or whatever. So we have to keep that aware. There's a magnetic north, and then there's a true north. We call it true north. True north is geographical north. We need to keep that aware. We have to be aware of that. And the next slide sort of explains that a little better, if I can pull it up. Try that. There we go. So we see on this chart, there's some amazingly diverse magnetic directions. So you're out over the Rocky Mountains, it is not pointing north. We have to make some corrections if we want to read charts correctly and for navigation as well. Happily, GPS and the fact that drones don't fly that far right now, it's not a problem, but it will be later when we start doing long-range drone flights, if and when we do that. It may not be economically viable at this point, but recall that there are other engines for drones that may extend our range by a great deal. So we want to have at least a knowledge or an understanding of this. On the chart, it will tell you, it will have these lines on a sectional chart, magnetic variation lines. So this is telling you, this line here, this is Marion again, this is true north. It's pointing to true, if I could draw a line straight, true north, or east, true west, etc., right? So these lines, latitude and longitude lines, are indicating true, actual geographical North Pole. This line here is showing us what we have to do to correct for that variation. So these lines are always going to be well, not always, but mostly slanted a little bit. So in order to fly north here, we have to add 5 degrees to our compass heading. A compass is a magnetic compass, right? It's going to point to magnetic north. So we have to add east is least, west is best. So west would be 5 degrees too, if you want to go to any heading. So if you want to head to the west here, your compass heading would have to be 275 degrees if you want to go that way. If you want to go exactly west, you'd have to steer 275 degrees because you had to add 5 degrees. These are called agonic lines. That's just merely the correction factor. And back to this magnetic, the VOR. We have a VOR, and notice it's pointing way over there. Well, we said that this is north, true. Why is this saying north is that away? Because that's magnetic. So these VOR navigational facilities are based on magnetic, basically. That's why there's a difference between the two. There's like, wow, it's a lot of difference. In fact, there is 12 degrees difference. There's the magnetic variation line, east. So east, you subtract. If you want to head north, here you have to subtract 12 degrees. Do we have another example here? Okay, this is basically it. So if you want to plot a course, true course, TC is true course, you have to add or subtract the variation to come up with a magnetic course. It'll tell you which way to fly. And right now you don't have to worry about it too much, but you need to be aware that there is a factor there that changes. Then we got another issue that comes up, is that your drone, you have, even if it's an electrical drone, if it has a fuel, liquid fuel powered, the engine is going to be a massive block of metal, and it's going to have some magnetic properties. But if it's a drone with a batteries and electrical wiring, it's going to have magnetic issues as well. The wires, electricity running through wires creates a magnetic field. So what manned aircraft have done, and I can conceive that this will eventually happen for longer distance drones, you will have a correction card for each particular drone, which will tell you that if you want to go north, yeah, everything's fine. But if you want it heading 030 degrees, you're going to have to steer 28 degrees. So now you've got to add not only the fact that the magnetic North Pole is in a different place, you're going to have to correct for whatever magnetic interference exists on your actual aircraft by going to one of these kind of charts. West is 270 degrees, right? But in order to do that, we have to fly 274 degrees. But that's not all. Then we have wind correction as well. If you just point the aircraft, and you've already may have noticed that as we go out flying, if you point the aircraft in one direction, the wind can make it drift off to the side. It's not that's just something you have to correct for, or be aware of anyway. We live in a world where large air masses are moving through. Even local air movements are going to distort the flight path of your aircraft. And we've talked about that before as far as ground speed, right? There's ground speed can go increase or decrease depending whether you have a tailwind or a headwind. Here's a case. Headwind, if you're going directly into the wind here, there's no correction at all except your ground speed will be lower. Whereas if you got a tailwind, ground speed will be higher. And then of course, if the winds, this is showing the wind going this way. If you're heading that way north, it'll keep going that way. If you're heading south, it'll keep going that way. So there's definitely, you have to make some corrections for wind. It may be unconscious, but for longer flights, we need to be more conscious about it. So basically, we'll calculate something and it will look wrong. If you just look at the chart, draw a line, and go in that direction, you may not arrive at the correct location, right? Because we'll end up not there, which is not good. So an example of a correction here is this here. All right, so we're heading on a course of 360. That's the line on the chart. So we have to head, depending on how much wind, a certain angle here, 15 degrees maybe. So we'd be doing the 360 would be 15 degrees, 345. We might have to be heading 345 degrees. Depending on, and it depends a lot on how fast you're moving and how much wind. Maybe more than you really wanted to learn. Okay, here's a diagram showing the ground speed as well. So, and this is vector geometry. You may have already been introduced to it at one point in high school, but we can draw things out in vector diagrams. True heading to airspeed gives you a vector of this, heading and distance, and you draw the wind. Where is it pointing, and what's the velocity? Is it hang on, I can spell. Direction and velocity. And then, so you write down the compass direction. Which way are you heading? Let's say this is 010 at 100 knots. And this is 110 degrees at 20 knots. Then you draw these lines out, and that means that you're going to be here at the end of that time, and this is going to be less. This line's shorter than that. This line's shorter than that line, so ground speed is going to be 90 maybe. I'm just pulling numbers out of my hat here. So you can calculate this out, and that's basically how we do a wind correction problem for manned aircraft navigation. I'm simplifying it, of course. A little more involved, but that's just a basic idea about a wind triangle. Okay, so I'm going to complete that now, and so watch those other 2 videos, and that will be it. See you next time. Bye.